How's exam 3? I'll have the sheet scanned right after lecture, and the score's up this afternoon. Now, to lay strong foundation for chapter 23 and understanding our main aim in chapter 23, which is learning how to devise explanations, rationale, for the strengths of Bronsted-Lowry acids and bases. Chapter 18, we talked about a number of different Bronsted-Lowry acids and bases and provided you with information regarding their strengths, specifically Ka values for the acids, Kb values for the bases. But at that time made no attempt to explain why the acids and bases we considered showed the strengths which they showed. Chapter 23, this is our main aim. To find out why the acids and bases which we have considered show the strengths which they show. To get started with this understanding, you have to be on top of periodic size trends, which I'm sure you talked about in 2045, but I don't know to what extent. I'm sure you learned regarding atoms, for example, A-family atoms. That as you go across a period left to right, like period number 2, lithium on down through neon, you observe a size shrink as you go across the period. Beryllium is smaller than lithium. Boron atom smaller than beryllium atom. Trend continues. But in most cases, the difference in size between the right side atom versus the left side atom is slight. In many cases, the right side atom is smaller, but only a little bit smaller. But by the time we go from lithium all the way to neon, we've looked at a bunch of size shrinks. The upshot of which is that a neon atom by itself is a good deal smaller than a lithium atom by itself. Why? In these videos, this issue is wrestled with in detail. Family size trends. A family again. We purposely avoid size trend considerations for B family atoms because there is no size trend for these atoms. Regarding B family atoms, like the first row, transition metals, scandium on down through copper. Zinc family is not really a transition metal family. That's discussed in chapter 23 at the start. There's no size trend, no size pattern. Manganese may be larger or smaller than chromium. I don't remember the data straight away. The iron atom may be larger or smaller than manganese atom. When you get d electrons in the valence shell, there is no more discernible trend or pattern in size differences. So the size trends which we consider are strictly for A family atoms, but that's very important. After all, most molecules by far are derived from B family atoms. Particularly, not B family, but A family atoms. For example, or particularly, so-called organic molecules. 10 million of these things now known. And we're finding new ones every day. Synthetic organic chemists are making new molecules every day. New natural product chemists are finding new molecules in the environment every day. And what are the principal atoms of which these molecules are composed? Carbon, hydrogen, nitrogen, oxygen. With just those 4 atoms alone, we're talking about millions of molecules. So ascribing size trends to A-family atoms is important, even though in so doing, we're neglecting a whole bunch of atoms that are part and parcel of the periodic system. But the chemistry of these A-family atoms is very huge compared to the chemistry of the other atoms, as we've just mentioned. Now, regarding family size trends, A-family atoms. Lithium, sodium, potassium, rubidium, cesium, francium. How do those atoms compare size-wise? They get progressively larger as you go from period to period, staying within the family. And what do we see regarding relative size? In most cases, we see a big difference in size. A sodium atom by itself is a much larger atom than a lithium atom by itself. A potassium atom by itself is a much larger atom than a sodium atom by itself. Now, these big differences in size tend to fade when we get near the bottom of the family. But so what? Because now we're dealing with elements whose chemistry is far less significant and far less important than the atoms near the tops of these families. Why is this? Well, this is my directive to you. I once again reviewed these videos yesterday, and I believe I've offered explanation of these considerations as well as I can do. So I don't see any point in repeating this stuff or attempting to do so. Furthermore, if you do what I'm asking you to do, look at these videos this weekend, take you a couple hours, big deal. That provides us with a whole lot more time to get at the stuff which we really want to get at in chapter 23, which I've already mentioned. Developing an ability to rationalize strengths in bronze-telluric acids and bases. Do it! Now then. A comment regarding information that you have seen in the syllabus. At least I trust you've seen it. Comment which says, when we get to the final exam, of course, in addition to the final exam, we also have special quiz number 3. I've already got the questions and problems in my mind for special quiz number 3, so all I got to do is assemble them. I do have to spend some time this weekend doing my income tax so I could avoid going to Leavenworth, someplace I do not choose to visit. Some of you may want me to be there, but that's your problem, not mine, because I ain't a-going. So after I spend my couple hours working up this tax stuff, I'll write special quiz number 3. But regarding the final, which will be to an extent comprehensive, and after I invent the final, I'll define its comprehensive nature. I'll tell you which past quizzes and exams to look at on a specific problem basis. I won't simply say everything we've done is fair game, because we have done a ton, and we got a ton more to do. So I'll try to define the nature and content of the final for you as specifically as I can. Of course, the stuff which we have so far not asked you to consider on exams will, of course, be part of the final. Stuff which we talk about today and from hereafter. But what's at issue here is your performance on the final. Given that it is comprehensive, at least to the extent that I shall so define. I've always been of a mind to pay a great dividend to those who perform quite well on the final, particularly if you perform quite well and you have not performed particularly well on exams and quizzes leading up to the final. Because it strikes me that if you do a good job on the final, you're saying to me, now I got it. I've got this stuff digested much better than I've been able to so far. So with that, if you impress me with your performance on the final, I will take that into strong consideration when I have to go through the process of writing down a letter grade for you and transferring such to the registrar. Now, as the syllabus says, this is not a negotiable issue. Don't you dare come to my office and say, how much do I have to score? Because if you do that, I'm going to say you have to get every question right or else you get a 0. How's that? I don't want you at all to behave like a budding lawyer. The only thing that matters is your academic performance. And I'm the judge of this, not you or anybody else beside me. That's the way it is when you're the instructor of a course. Don't come and say, geez, I've sweat blood. I've made thousands of hours of effort. Fine if you have. But it's got nothing to do with academic performance and is not a measure of academic achievement. It has no bearing on grade, therefore. So your job is to simply do the very best you can on that last exam. And for those of you who do, particularly for those of you who do, and it's much better performance than what you've done previously, I'm going to say, good. This person has convinced me that he or she is now on top of the stuff, or at least is now much better in touch with the stuff than previously. So if I were to treat you by strictly points earned, instead of getting a C, you might get a B. Instead of getting a B, you might get an A. Depends. I've even had people jump up by 2-letter grades on this because of a very strong performance, but it's your job to do the performance. Then I have something to think about. It's your job to give me something to think about. And that will not be achieved by your walking into my office and telling me some story. The only thing that matters is your score on that last exam. Keep in mind that this method of operation by me cannot hurt you at all. Because the worst that can happen is you get treated, just as the syllabus says, by total points. And if your performance level on the final is in parallel to what you've been doing so far, that's the way you'll be treated. So let's finish electrochemistry. Concentration cells. Interesting cells. Cells which you should recognize in short order fashion are not used to develop large E cell values, operating potentials. An example of a net cell reaction for a concentration cell. What does this reaction show us? It shows us that a reducer in fact reduces its own conjugate oxidizer. If I put a copper strip in copper sulfate solution, electron transfer is taking place. But with the copper strip in the copper sulfate solution, the electron transfer never changes net composition of the system. So there's no usable or derivable electrical energy from that system as I just described it. A strip of copper standing in copper sulfate solution. But let's talk about a strip of copper standing in copper sulfate solution and a different strip of copper standing in a different copper sulfate solution. as suggested by this brilliant Van Gogh diagram. Parallels the Mona Lisa in artistic stature, don't you think? There. I initialed it for you. Its value just went up immensely. What's E0 for a concentration cell? Zero. You got a given half reaction occurring in this half cell in which oxidation occurs, and exactly the same half reaction but traveling in the opposite direction in the half cell in which reduction occurs. What's delta H? Zero for a concentration cell. Got to be zero. Rather than delta H zero for a concentration cell, what's delta H for a concentration cell? What does change in enthalpy in the main measure? Bond improvement versus bond disimprovement. Well, here, as we produce hydrated copper ion by oxidizing copper metal, we're making copper-water molecule bonds. And as we reduce hydrated copper ion, we're breaking copper-water molecule bonds. And I guarantee that for a concentration cell, the number of copper-water molecule bonds made has got to equal exactly the number of copper-water molecule bonds broken. In other words, however many moles of hydrated copper ion we produce has got to equal the number of moles of hydrated copper ion which were reduced. So what's delta H? Zero. What's delta S? Zero for a concentration cell. Because this is change in entropy under standard state conditions. And standard state conditions mean hydrated copper ion is present at 1 molar. Well, if I got hydrated copper ion at 1 molar here and hydrated copper ion at 1 molar here, am I going to get net electron transfer? Nope. Well, then what's delta G zero? Zero. I mean, if E0 sells zero, this delta G zero got to be zero. Now then, if we get net current flow for an operating concentration cell, then it must be true that delta G is non-zero. What accounts for this? What thermodynamic function for this concentration cell system accounts for delta G being non-zero?
Different concentrations.
I want the thermodynamic function. It's got to be delta S, isn't it? It's the only part of this puzzle which we have yet to consider. So delta GR is minus because delta SR is plus or minus? Plus or minus? Plus. That's a favorable change in entropy. So call it entropy of mixing for the following, or based on the following example. If in a beaker I pour 100 milliliters of 10th molar copper sulfate solution, and in the same beaker I now pour in 100 milliliters of 1 molar copper sulfate solution, okay? Then I walk away, allow this system to stand by itself, and I come back in a month. What will be the contents of the beaker? Will it still be 100 milliliters of 10th molar copper ion at the bottom and 100 milliliters of 1 molar copper ion at the top? Will that be the case? Absolutely not. If I take 10th molar sodium chloride solution, put it in a beaker, and 5 molar sodium chloride solution, pour it on top, will the 10th molar sodium ion stay unmixed with the 5 molar sodium ion? 10th molar chloride ion, 5 molar? Hell no. The natural drive in nature, thermodynamically speaking, from a change in entropy standpoint, is to mix up stuff. That creates a state of higher entropy. All right? So the driving forces has favorable change in delta S. So here's our concentration cell with one consideration yet to be made. There's a fancy light bulb. Now if we're going to light a light bulb with this kind of concentration cell, where I've connected the two cells with this salt bridge, given that the resistance of the salt bridge is enormous, if I put an LED in there, I might get an observable glow. A bulb which draws very, very little current to make it light up. But my intention is to make this very low current requirement bulb to light up. That means I got to have electrons flowing through it. I have 2 copper sulfate solutions, 1 molar and 100th molar. Now you know that from an artwork standpoint, it's standard practice in drawing a cell that the left cell be anode or cathode? Okay. So if I want this cell to have the left cell as the anode compartment and the right cell as the cathode compartment, which means the electrons will flow this way through the bulb, which copper sulfate solution do I put in this cell? Either put the 1 molar copper sulfate solution or the 100th molar copper sulfate solution. Which one do I put in the left side cell if I want the left side cell to be the anode compartment? All right, I heard a couple of voices say 100th molar. How many wish to support that proposition? Now, since everybody's obligated to vote, I will now conclude that the majority vote to put 1 molar copper sulfate solution in the left side cell, which means the majority is dead wrong. Because as oxidation occurs, which is what occurs if this is the anode half cell, as oxidation of copper occurs to become hydrated copper ion, what happens to the molarity of initially 100th molar copper ion? It increases. And if reduction occurs, as it will occur in the cathode half cell, what happens to the molarity as electrons transfer to initially 1 molar hydrated copper ion? Decreases. But if I was going to believe that with the 100th molar copper ion here and the 1 molar copper ion here, that this is the cathode half cell being the half cell at which reduction occurs, then this copper ion would be getting reduced while this copper ion would be getting created, which means I'd have a strange concentration cell because as it operated, the 1 molar molarity would get larger as the 100th molar molarity would get smaller. That's like putting our 100th molar copper sulfate solution in the beaker, and then on top of it the 1 molar copper sulfate solution in the same beaker, and have the copper ions net transfer from the lower concentration solution at the bottom to the higher concentration solution at the top. And after we come back in a month, we analyze the beaker, and the top solution is more concentrated than it was, and the bottom solution contains no copper ion. You think you're going to find that? Hell no! So the lower concentration of the ion, that's the ion in question in the concentration cell, is always found in the anode half cell. Enough said. Now, how do we get E cell? Well, this is 0. And for this system, N is 2. So what's log Q? Can I cancel these copper ions? If I cancel it, I got 1. And then I got nothing. E cell is 0. Because the log of 1 is 0. So the molarity up here is here's the system. Which of these copper ions, the reactant copper ion or the product copper ion, is the copper ion in this, the anode half cell? Which of these copper ions is in the anode half cell? Reactant copper ion or product copper ion? Product copper ion, you betcha. So here I'm taking the log of 10 to the minus 2. And the log of 10 to the minus 2 is minus 2. And minus 2 times a minus gives me a plus, doesn't it? And that's how we get a net non-zero delta G value and a net positive E cell value for a concentration cell. Galvanic protection. I expect you've heard about this. For example, these oil rigs that you find in the Gulf of Mexico and places like that. They're usually mounted on big iron poles. Given that iron is the cheapest and strongest material available from Mother Earth for common construction purposes. Iron, strong and cheap because it's abundant. But there's one problem, chemical problem with iron. It tends to rust readily in moist air. Air got oxygen in it and moist water. Because when iron, base metal iron, is in the presence of moist air, it readily is oxidized to this stuff. Call it iron rust. Have you any familiarity with iron rust? Any of you doing any work in the Simon 10 and 46 laboratory? Hydrated iron plus 3 readily reacts with hydroxide ion or ammonia or, practically speaking, any basic solution to make that stuff, because that stuff is damn stable thermodynamically. Unfortunately, that stuff is damn unstable structurally. Like graphite is thermodynamically very stable, but structurally it's not nearly as stable as carbon diamond. Thermodynamically, that stuff is really stable. But this stuff has very little structural integrity. So when iron is oxidized to this stuff, this has practically no lattice strength to speak of. It crumbles and falls off. Well, what happens? I've now exposed new, fresh iron to the oxidizing environment, and the oxidation of iron continues so long as the moist air environment is there. So where do I run the greatest risk of oxidizing an iron pole if it's supporting an oil rig in the Gulf of Mexico? Here's this iron pole. Where is it most likely to be oxidized? Right at the level of the Gulf of Mexico, right? Because that's where this iron is in contact with water and the air above it to get oxygen, right? Now, what do we usually do to preserve this iron? Well, I think the iron poles are commonly in contact with magnesium strips. But the simple, for home construction stuff, we usually galvanize iron. Galvanize is the word given for this galvanic protection procedure, because it's named after Luigi Galvani, famous electrochemist. So galvanization is the name given to a process where I take the metal that I want to protect, like iron, and I coat it with a more reactive metal. Now that may sound strange, because we know the more reactive metal will be more readily oxidized. That's true. But what's the benefit of oxidizing zinc rather than iron if I have iron galvanized with zinc? Well, when I oxidize zinc, I make this stuff or this stuff. Now I'm sure that initially I'm going to make this stuff. And this too doesn't have very much structural integrity. But if I understand the chemistry of this correctly, this readily dehydrates and becomes this stuff, which on further dehydration will become this stuff, and either of these zinc compounds are structurally stable. So they stay on the surface of the iron and protect zinc as well as iron from any further oxidation. Because this is oxidized zinc. Call it zinc rust. But this is stable zinc rust. If the iron hydroxide, again, if I understand the chemistry of this, if it starts to lose water, it'll convert to this. Ferric oxide with X water molecules, where the number of water molecules is ill-defined. But this stuff still has no structural integrity, so it still crumbles and falls apart. But not these. These stay in contact on the surface of the galvanized iron and keep it protected, because these have structural integrity. And that's galvanic protection in a nutshell. Same with magnesium. Magnesium will be readily oxidized to magnesium. Well, I would bet first this. You have familiarity with this stuff, don't you? By where you work in 46L. But this stuff behaves like the hydrated zinc hydroxide. This readily loses water to become this, and this loses water to become this. Magnesium oxide, pretty stable stuff. Principal component of fire brick. You think fire brick is capable of withstanding high temperatures, for example? Have you seen lately your fireplace construction falling apart? Not really. Magnesium oxide, pretty stable stuff. Now then, the last issue of consequence in chapter 22 is how to derive E0 for new half-cell reactions. This is discussed in detail in the notes, beginning on page 22, 27, and carrying on through the end of the chapter, which is just a couple more pages. Well, let's jump right to question 2232. This half reaction you will not see contained in our half reaction table. I'm thinking to put it there because it's a half reaction I like to refer to rather regularly, but then I'm going to have to invent a new question 2232. But I can do that. Iron being oxidized to hydrated iron plus 3. Now in our table we have iron being oxidized to hydrated iron plus 2. We have iron being oxidized to this, and we have this being produced by oxidation of hydrated iron plus 2. But this half reaction itself is not in the table. So if I want to get this half reaction, how do I get it? There's two ways to do it. First, by using the information in the table. This is discussed in the notes. Take a look at table number 2 and tell me the half reactions which, if I add them together, I'll get this half reaction. Take a look at table number 2. So I don't have to write this again. I'm going to call this half reaction circle star. Notice if I take these two half reactions that I've written and add them up, I get half reaction circle star. These half reactions are in our table. Tell me the E0 values. Plus 4,4? 7,7? So this leads to the question. What's E0 for circle star half reaction? And here comes the problem. When I couple half reactions, I cannot get E0 for the net half reaction by adding the E0 values, because I do not generate a system where there's no net electricity involved. So what do I have to do?
Could you find the delta G's?
That's what we have to do. What we can do is to add the energy changes for these half reactions. That's what we can do. So we get out our recipe. And apply it to each of these half reactions. I got the E0 value. N is 2. F is the Faraday. And when you do this, you don't really need to put the Faraday in there, because you'll see it'll cancel from the final arithmetic we have to do, final arithmetic step. So let's call this 1 and this 2. And take advantage of the fact that this relationship is true. Delta G0 for the half reaction in which we are interested, half reaction circle star, is equal to the sum of delta G0 for 1 plus delta G0 2. So, after I calculate delta G0 for the half reaction in which I'm interested, then I go back to delta G0 equals minus NFE0 and compute its E0 value. But if the data are available, there's an easier way to do this. To what data do I refer? So I'm going to write this down. If data are available, what is the easier way to get E0 for a new half reaction? Answer: use data from table 1. Yeah, that's right. You remember how we succeeded to get Ka values for very strong acids? By using appropriate data from table 1? These calculations, we did a couple of them at the end of chapter 21. Well, now at the end of chapter 22, we're going to go back again to table 1 and recognize that if the data are available, this is the easier way to get E0 information for half cells. Should we be interested in a half cell for which the E0 value is not tabulated or not available in our table, whatever the case might be? Consider this. Or this. Those are two half reactions, neither of which appear in our table. So what my charge is to you, to get us finished with chapter 22, is to calculate, using table 1 data, E0 for these half reactions. Reminder, if I'm going to get delta G0 for this thing, and I don't have delta G0 available for this thing, delta G0 sub F super 0. I've got to get a handle on delta G sub F super 0 for water solid. And if you look at table 1, you will not see water solid and corresponding thermodynamic data for such in the table. Why not? Because the data in table 1 have been tabulated at what temperature? 25 centigrade. We don't find water solid existing at 25 centigrade. So how the hell can we do this? We'll pick it up from this point next time. And I will expect you to know how to do this.